All right, we're going to start reviewing for the semester test. Here we go. We have a lot of things to try to cover. Okay, so far we've covered kinematics. Second thing that we've covered, dynamics. Third thing that we've covered, circular motion, right? Circular motion and gravitation. Gravitation. Always have a positive mindset. Imminent failure is not the way, it's not the physics way. And the fourth thing that we basically just started covering is energy and work, which means there won't be a whole lot of questions on there dealing with that, but I'll probably tack a couple of them on there. All right, so I actually want, normally with my 9 weeks test, I normally try to not make them an AP Physics exam because I try to make the questions I try to make them a lot easier than the AP Physics exam questions. So there's going to be a lot of questions that should not be as difficult, kind of like the 9 weeks test. The 9 weeks test questions weren't as difficult. Does that mean that everybody's going to make an A? No, absolutely not. But there's, definitely some things that we need to try to go over. Let's tackle these from beginning to end. So, we've got our kinematics, our dynamics, our circular motion and gravitation, and our energy and work. So, I'm going to take a deep breath here and try to think everything that I know about kinematics. And let's see. If I were to have like 5 minutes to save the world and be like, hey, tell me everything that you possibly humanly know about kinematics, I would say, all right, if in 10 or 15 years, the main things I would want you to remember is the main difference between like constant motion and acceleration. So there are two basic mindsets that you have to go through here. And if you've got constant motion, then we're going to have velocity is equal to your displacement divided by your time. If you have acceleration, you have the kinematic equations, which is everything is going to be available to you on the AP Physics formula sheet. So VF squared equals VI squared plus 2AD, fair game. VF equals VI plus AT, fair game. Displacement equals VIT plus 1 half AT squared, fair game. The forbidden equation, VI plus VF over 2 times time. This one is not on the kinematic equation sheet. So take that with a grain of salt. You won't have this one right in front of your face. You would have to have that one memorized in order to be able to do that. Yeah, and that's perfectly fine. There's nothing wrong with that. If you take an object and you drop it from any particular location, the acceleration is always going to be negative 9.8 meters per second squared. You can also use negative 10 and get away with it, and that's perfectly fine. It's close enough and it'll be fine. I think I don't know if I'm going to have enough time to throw all of this stuff into Canvas, but if I do, I will have a tolerance of plus or minus 5% from both of these answers. So I'll take the low, I'll take the high, and I'll say plus or minus 5% from those answers. That would be the correct answer. Okay. 5% is a very generous number, so you would have to be way off in order to get the question incorrect. You're not going to get it by like rounding difficulties or anything like that. Okay. Right, like if you like, yeah, if you're like instead of using 9.8, you're just like 9. That would probably make a difference, but the difference between 9.8 and 10, I really wouldn't worry about it too terribly bad. Okay, there's also the concept of two-dimensional motion. So there's one-dimensional motion and there's two-dimensional motion. Um, Right. So like whenever you take an object and you throw it like in the air, the x direction is constant. So once you leave that locations, like if you're throwing something, once it leaves your hand, that force stops immediately. So you continue to go at a constant speed this way. So in the x direction, you're just using velocity is equal to distance over time. However, in the y direction, you have to use the kinematic equation because there is acceleration involved there. Basically, we say we are ignoring wind resistance a lot in this case. So as you go up, the velocity, oh, hang on. I think I might actually have this backwards. Hang on. What am I doing here? I'm doing this backwards. Hang on, sorry. I'm going to try this, do it the right way. Your velocity is going up this way, and then it shrinks down as you go higher up. At this point, it's 0, and then when you go this way, it starts to go down. And it goes to the same velocity as its symmetric counterpart. It's just on the opposite side. So if this was plus 20 meters per second, this one over here would be like negative 20 meters per second. The acceleration during this entire thing in the y direction is always negative 9.8 meters per second squared. The acceleration in the x direction of any projectile is always 0 meters per second squared. 0, none, nada, absolutely none. That one is tough for people to remember. Some of the things that we also did was the kinematic graphs. So this is like the big bread and butter. If I want you to remember this like 10 years from now, the next thing that I would want you to remember is the kinematic graph parts. So if we were to take graphs of like velocity or displacement versus time, these things are real deals. So if we're doing graphs, you could actually graph that motion. So I'm going to say, let's just make a graph of displacement versus time, just to make a quick sketch and make it do like this. Yomp, yomp, yomp. From this period of time, there are 3 basic locations here. There's this turning point, and then there's this turning point, or maybe I should say inflection point. I don't know. Something happens at these locations. The motion is changing. So we can basically break this up into 3 main events. So during the first event, what's happening? Really? I'm moving? What am I moving? Like, describe my motion. Okay, so we're moving forward. That's true. That's true. We're moving forward at constant speed. How do we know that it's constant? Yeah, so like if the velocity versus time graph slope is 0, then you're moving at a constant speed. For a displacement versus time graph, if your slope is some number, then you are actually going some constant speed. This is distance or rise over run, y over x. So if the slope of your line is positive, you're moving forward at a constant speed. If the slope of your line is negative, you're moving backwards at a constant speed. So it's the same thing, except in this one we're moving backwards at a constant speed. Okay, at constant speed. In the middle part, what's happening? Yeah, there is no motion. No motion, standing still. Okay, so not too bad. Let me do a velocity versus time graph, and we'll move on from this. So I don't think I'll have any acceleration versus time graphs, but you never know. That could be terrible to you guys. I haven't written the test yet, so velocity versus time. So if we have the same thing that happens here, I'm going to do this. I'm going to go whoop, 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 whoop. There we go. All right, so how many events can I break this down into? Okay, there's 1, 2, 3, 4 events. So I'm going to call this one 1. I'm going to call this one 2. I'm going to call this one 3. I'm going to call this one 4. All right, what's happening in event number 1? Okay, we know that we are accelerating, and it's a positive acceleration. Okay, so we're accelerating in the positive direction. What about event number 2? Constant speed. Okay, what about event number 3? This is a negative acceleration. That almost looks like Akil. It doesn't even look like negative acceleration. What about the bottom one? Okay, this one is a constant speed as well. Now, if I were to try to calculate the total distance that was covered, what could I do? Yeah, I would have to find the area under the curves in order to find the total displacement that got traveled between. So I would have to add that triangle, I would have to add this rectangle, and then I would have to add the positive and negative or the negative triangles here as well. And then I would have to add this last rectangle down here at the bottom. I'd have to add all of these together. In order to actually do that, we would need numbers, but since we're just flat out reviewing for the semester test, I'm going to just leave it as concept only. If you need examples, you can go back in your notes or back in my YouTube videos, either one, and find them because we've literally done them before. So I'm not going to waste our time since we've done everything like this. So you should expect a couple of questions dealing with kinematic graphs, either displacement versus time or velocity versus time. Either one of those is just fine. Okay. So so we have a let's see here. Kinematics. Do y'all have any other questions about kinematics? Okay. Dynamics time. Everybody's favorite. Dynamics. You have oh. Like I don't even know what that is. Oh, dynamics is forces. Anything that we dealt with that dealt with forces was dynamics. So yeah, the best thing that I wanted to try to go with is the first thing is know how to actually like write diagrams. So free body diagrams and how to like label forces. That's like the first basic skill. So if you don't know that one, that's the first thing to do is like how do I actually record forces happening on an object? That would be using free body diagrams. After that, you would try to use that in Newton's laws first, second, and third. And then after that, we would go into some laws dealing with systems. And that's basically the three big sections that we did. So the first one is like guppy mode, and then the second one is like, I don't know what's above a guppy. This is like a frog. And then like systems thinking, you've gotten big brain if you've gotten the systems, and you can do everything in forces with that knowledge. Okay, so free body diagrams are very easy. You just take the object and you move it to a dot. So if there is a book like or a box standing on the ground and it's being pushed this direction, instead of actually drawing the box out, you would just make it a dot and you would put all of the forces acting on it. So in this case, if there's friction, there would be four forces acting in that direction. We would have a force of effort, which we'll call Fe. There would be a normal force pushing up on the floor. There would be a force of gravity, mg, pushing down. And then there would be a force of friction pulling it back. If it's moving at a constant speed, then the effort force and the friction force are going to be balanced with each other. If it's not balanced, then there's going to be acceleration, either a positive acceleration or a negative acceleration. If the effort force is greater than the frictional force, there will be a positive acceleration. If the friction force is greater than the effort force, there will be a negative acceleration. It all depends on what direction that it's actually going. Using these free body diagrams and taking them, moving them into specific places, that is how you would do that. Newton's laws come in three flavors. So we have three different Newton's laws. There's Newton's first law, Newton's second law, and Newton's third law. For Newton's first law, it's very straightforward. It basically just tells you an object in motion will stay in motion. An object at rest will stay at rest unless disturbed by an outside force. This is also known as the law of inertia. So I'll just write out inertia, and that basically means your tendency to either stand still, or if you're moving, your tendency to keep moving in one particular direction. Okay, that's Newton's first law. So I'll put first law, one. Newton's second law is going to tell you that the sum of the forces acting on any object is going to be equal to the mass of the system of objects, or if it's just one object, the mass of that object, times the acceleration on the object itself. We use the crap out of this one. Newton's second law is like the number one law to know. Out of all the flavors, the favorite flavor is by far Newton's second law. Okay? And we use this one like constantly. Newton's third law is going to tell you that for every action, there's an equal and opposite reaction, and those forces are acting on different systems. Okay, so if you were to do a push and a pull, that push and pull are going to exist in two different areas. This is how we actually accelerate, and that we don't get like different, and we not everything just cancels out to zero. Okay, so this is the action reaction pair law. Action reaction pair. So if you have a cart and a horse is pulling the cart, which looks like a really big stick figure, um, that is quite a horse. There, it's got some ears too. Um, whatever. So there's always that fundamental question. Well, yeah, and so like if the horse is pulling on the cart, but the cart is also pulling on the horse, how does it even move? And the answer is, well, these are acting on two different systems, okay? So whenever you pull the cart is going to get pulled this direction, but on the other side, the cart's wheels are going to exert that force on the ground to push it this direction. So is there an equal and opposite reaction pair with everything? Yes, but those things are going to act in two different systems. So, like for example, another one is if you take if you're out in space and you're just like stuck in the middle of nowhere, and you're like, oh crap, I don't have anywhere to go. If you take an object in your hand and you throw it, whenever you throw the object this way, it's actually going to push you back this way because you exert a force on the object, and the object also exerts a force on you. Notice that these are two different things that is the force is being exerted on. So since there are two different things that the force is being exerted on, they do cancel out to zero, but motion happens because they're happening to two different systems. Okay? So the action reaction pair is how things do the move. The force equals the mass of the system times the acceleration is what we use to try to find out how things actually accelerate. And Newton's first law of inertia basically just tells you an object in motion is just going to stay in motion. Things don't magically just stop. They have to accelerate and decelerate in order to do that. Okay? We can try. Do y'all want to try an example or you want to just move on? Okay, let me give y'all a couple examples. Inclined plane example with dynamics. So if you've got an object that's moving down the ramp and we have an angle theta, this object is moving down said ramp and it's got a mass of m. Then the way that we would do this is we would draw out the line of action. So the line of action for us is this ramp is going to be moving down this hill this direction. We would draw out the forces. So since I don't want to crowd this area over here, I would make a free body diagram. When I make the free body diagram, what forces do I have acting on this? Okay, we have gravity pulling straight down, right? mg. What else do we have? We have the normal force that is not pointing straight down. We have the normal force going this direction. Okay, what else do we have? Okay, you want to include friction? There's a frictional force pushing this way. Okay, now these are only three forces. There is no effort force, and that's because the line of action is moving down this direction. So if we want to find out what the force is pulling down the ramp, we're going to have to take the things that are not perpendicular to the line of action, and we're going to have to make them perpendicular to the line of action. So I'm looking at normal force. Yeah, sine cosine stuff. I'm looking at the normal force. Is the normal force okay? Does it look legit? It's legit because it's 90 degrees. Okay, I'm looking at the friction force. Is the friction force legit? Yes, because it's at 180 degrees, so it's like, in a straight line path to it. I'm looking at mg. Is it legit? No. mg is not legit because it's not at 90 degrees to the line of action. So what we have to do is we have to break it down into its components, and we're going to make it legit. Okay, so this one, the normal force, this is going to be mg. Let's see, where's our theta here? Theta's down here. So for our right triangle, that's going to make it right here. So this is going to be mg cosine theta. And this one going down the ramp is going to be mg sine theta. So the force of friction, if we were to try to add these things up, the sum of the forces is equal to mg sine theta minus force of friction equals m, mass of the system, times the acceleration. Okay? Now, I did this to where friction is negative and going down the ramp is positive. Are y'all okay with that? Y'all okay with that? All right. So that means that down is positive, and I'm okay with that because this would be the positive direction and this would be the negative direction. Okay, so we got mg sine theta minus the force of friction is equal to mass of the system times acceleration. The force of friction has a actual formula for it. I can't just write f of f. So that would be mg sine theta minus friction is fun, so that'd be mu n, and that's equal to the mass of the system. Since it's just a block, I'm just going to write that as m times acceleration. And there we go. The n in this case is equal to mg sine theta. The n is mu mg cosine theta equals ma. So if I wanted to try to find out what the let's see what we got here. What we got here? Did everybody bring mass to the party? I think everybody brought mass to the party. So the first thing I see is m. Bye bye. Bye bye. Bye bye. And the good news is that automatically solved for our acceleration. So our acceleration is just going to be g sine theta minus mu g cosine theta equals a. That would be an example of an action, or sorry, using one in dynamics. Another one that I really like to use is the Atwood machine, where you have one going up and then the other one going down. That's another favorite one that I like to do. What's up? I would have to have it, in order to find the coefficient of friction by yourself, you would have to have something given to you. So, like, I would have to give the acceleration to you in that case. So, if there was a circumstance whenever I said, hey, this object is going down a ramp, it starts off at 5 meters per second, and then it goes down to 10 meters per second by the time it hits the bottom. You could do the kinematic equations to find the acceleration, and then you could use that equation to find the coefficient of friction. We only have an hour for this semester test, so I don't think I'm going to do that to you because we just don't really have a lot of time. Yeah, you only got an hour to do the whole thing, so I mean, like, I can't go crazy. I got to keep it like real simple. I don't want to go. I say keep it real simple, and I've got like a bunch of math mumbo jumbo on the board. Go figure. It's generally how it works. Um, okay. So, questions so far? Everybody alive? You want me to do an Atwood machine one? Move on. Move on. Okay. Systems thinking is doing dynamics problems, but it's doing dynamics problems with more than one mass attached to it. So that means that the mass of the system would actually change. So that means that technically the Atwood machine would count as a systems problem. What's another thing that would count as a systems problem? How would I do this to you guys with the systems? Um, I'm pretty sure that the Atwood machine would be like the only way I'm going to do that to you guys on the semester test. So I'll just write down Atwood machine here and then I'll move on. There are examples. We have worked examples of that in class. We've done it several times before. So I'm not too worried about it. If y'all don't want to go over it, that's fine by me. Let's see. Circular motion and gravitation. Let's go on with our lives. Circular motion and gravitation. Go back to the big concept. So circular motion first. The big deal with circular motion is that if you have forces can be centripetal, and centripetal is like a flavor of forces. So that's like centripetal versus a linear force. Most of the forces that we cover in, or sorry, all of the forces that we cover in dynamics are linear forces. In circular motion, we start to learn that there are centripetal forces that go along as well too. When you take something and that object moves around in a circle, we make several different assumptions about that circular motion. Assumption number one is we assume that whenever it goes around in a circle, we assume that it does so at constant speed. That is not always how life works, but that's what we're going to assume. That means since we can make that assumption, there's a couple of things that we can say about it. Thing number one that we can say about it is that the centripetal acceleration of an object is equal to the velocity squared divided by the radius of the circle itself. So if you have a radius in the circle, that radius is on bottom, the velocity squared is on top. We can also say that because of that, there is a centripetal force, and that's equal to the mass times the centripetal acceleration, which would be mv squared over r. We could also take the velocity, and the velocity can be written as a different way. The circumference of the circle, 2 pi r, divided by the revolution time, which would be capital T. If you use little t, it's going to be okay. It's just most of the time if you deal with something that constantly repeats, it's in periodic motion, then we usually give it the prefix, or so the variable capital T. There's no other reason why. Like the big T is usually for repetitive stuff, and the little t is usually for like time intervals. Okay. Um, let's see here. We've got this. We've got this. We've got this. Dynamics included in circular motion deals with like if you're doing things like a loop-de-loop. Whenever you're doing the force diagrams for them, as you're moving inside the circle, the normal force normally is what acts as the centripetal force. So the normal force is normally what points inside the circle. So as you're going around here, this normal force is going towards the center of the circle if I could actually draw straight lines. And this center-seeking force, in the case of like a loop-to-loop on a track, that would be the normal force. If you're taking an object and you're spinning it around on a string, your centripetal force would be the tension on a string. There's probably a couple of other examples too. Um, let's see, if you're at the top of a hill and you're going around, that gravity would be the centripetal force holding you down. So like if you're on a bump like this, and it goes like that, whenever you're at the very, very top of the hill like this, the force of gravity is usually what keeps you down like this. As you keep going down this way, this is a little bit different though, because this doesn't really keep you in like a full circular motion. Because as you go down this way, gravity is going to start pulling you down and accelerating you, which kind of breaks this whole notion of going at a constant speed to start with. So if you're ever dealing with this problem, the only time that I would actually bother with it is if you're at the very, very tippy top of the circular hill, not at any other place, because then you would either be decelerating or you would be accelerating, and that makes life a little bit more difficult. It's not a straightforward problem at that point. Okay. Let's see here. Centripetal versus linear. We did the 2 pi r over t. Here's a couple of dynamics problems with it, and here's the formulas that we would use for it. The big lab that we did here was the rubber stopper lab, where we moved the rubber stopper around our heads and tried not to hit ourselves, and we tried to find the centripetal acceleration acting on them. Gravity was kind of like one of the last things that we've done. And there's a couple of different things that are involved with gravity. If you're not dealing with a circular motion type concept and you're just dealing with two large bodies that are gravitationally attracted to each other, the force of gravity between the two objects is going to be the gravitational constant times the product of the two masses divided by the distance between them squared. So that's GMM over D squared. Sometimes I call it R squared instead of D squared, but f of g is equal to this. The g is given to you on the formula sheet. It's 6.67 times 10 to the negative 11th, and I believe that's Newton meters squared per kilogram squared, in order to cancel out all of the units on the top and on the bottom so that you're just left with newtons. The two masses would be the masses of the two very, very large objects that you would use to put them in gravitational force with each other. And that would be if you're dealing with a linear case. These two objects would move towards to each other. I love to use force of gravity problems and then manipulating the variables. So like for example, if you have a force of gravity and this one is big M and this one is little m, what would happen to the force of gravity if I made this side 2 times greater and the mass just suddenly got doubled on it? What would happen to the force of gravity down here? How much would it increase? We would plug it in. This would become 2m. times m divided by d squared. So how is the left equation and the right equation similar? Yes. Do they have an m? Do they have a big M? Do they have a G? What are they missing? What's this one missing? Okay, so this 2 is on top, right? So this force of gravity over here would be 2 times greater if this mass gets on top. So if this force was originally 500 newtons with 2 times the mass over here, it would become 1,000 newtons. So this 2 is what actually is going to make the difference between those as well. If I took this and I halved the distance, so instead of having twice the mass, if I said, okay, instead of having d, we're going to have 1/2 d, what would happen to the force of gravity between the two? Take that number and plug it in. They have everything in common. They have a g, they have a capital M, they have a little m, they have a d squared, but they are missing, the big thing that they have different is that 1/2. What does that do to the entire problem? That is very true. If you're dividing by a smaller number, your answer is greater. So that's going to become 1/2 squared is really 1/4. And if you divide a number by 1/4, it's really the same as multiplying it times 4. So because of this 1/4 at the bottom, this is really the same thing as 4 GMM over d squared, which means that if you half the distance between these, the force of gravity is going to become 4 times greater, and that is because the distance squared is what the dependency is for gravity. So as you get further away, it gets weaker squared. As you get closer, it gets stronger squared. So the strongest gravity that you'll have is the shortest distance away between the two center of masses of the objects. Okay, let's see here. That is if it's not going in a circle. If it is going in a circle, then we have to do the Kepler's Law derivation. And we have to say, all right, if you've got an object moving around in a circle and it's going around this way, around the orbit, like so, then we would say, oh, okay, well, there's only one force acting on it. That's the force of gravity pulling it this way. We can't say that there's a normal force because there's no surface for it to act backwards on. We can't say that there's friction because space is very low friction. Okay. Does it hit often does it hit some gas molecules every once in a while? Yeah, but compared to the mass of the object, we're not really going to worry about it. So what we would say is we would say, all right, well, according to this law, there is a mass times acceleration. So we would say that, well, okay, what do we have here? Our centripetal force is the gravitational force. So the mv squared over r, centripetal force, is going to be equal to big G times big M, little m, over the radius squared. And when I say radius, I mean radius from the center of mass of the planet to the object itself. So this would be the radius. Let's see. The radius is going to cancel in one side, and we can rewrite the velocity as, let's see here. What do I want to cancel? Let's just go ahead and cancel one of these. And everybody brought mass to the party, so bye-bye. That's going to make those go away. That leaves us with v squared is equal to gm over r. Okay, I'm going to go ahead and take this velocity and say that that's 2 pi r over t, and I'm going to square it. That becomes 4 pi squared r squared over t squared. So 4 pi squared r squared over t squared is equal to g times big M divided by r. We can take this r and move it over to the other side. So what happens is we're going to get a cubed for the radius, and we're going to get a t squared for the period. So I'm going to say that, yeah, I'll go ahead and put it over there. 4 pi squared r cubed over t squared equals g times big M. Now, what we normally want to do is we're going to take everything that is a constant value that's not going to change, and we're going to move it over to one side of the equation. So 4 and pi squared don't really change. The universal gravitational constant and the mass of the object that it's rotating around, or revolving around, I should say, don't really change. So I'm going to put 4 pi squared over here, and I'm going to say on this side this is r cubed over t squared. Okay, this is the Keplerian constant. This tells you that no matter what, everything that goes in a circle around this center object is going to be proportional or related to r cubed over t squared, because that gm over 4 pi squared does not change. So as the radius squared, or sorry, as the radius cubed changes, the only thing that can change is going to be that t squared, which is where we get Kepler's laws of motion in. Okay, so Kepler has three laws. This one that we just talked about right there, this is his third law. Okay, the other two laws that he made were really, really easy ones. His first law was that all orbits are elliptical, which means they're ovals. Except a circle is an ellipse with an eccentricity of 0, so you can't quite call the circles out, but there's really no such thing as a perfect circle anyway, so there will always be a little bit of eccentricity involved. Second thing is that objects, all orbits cover equal areas in equal time. Okay, equal areas in equal times. Oh, did you say you're having a moment? Oh, okay. All right, so the third law, you could write it like this with this gm over 4 pi squared, and that's one way to write it. The other way to write it is to say that you could write it as a proportion if you have two objects that are rotating around the same body. So you could say that the r cubed over the t squared of one object is equal to the r cubed over the t squared of the second object. So that would be useful if you had two things that were going around and you could make them relatable to each other. Okay, so their radius cubed divided by their period squared are related to each other and you can set them equal to each other. You can do it this way or you can do it this way. Okay, the way on the right is useful if you have a, go ahead and put that in there. The way on the right is useful if you have a center, if you have knowledge about the center of mass of the object, like the sun or the star that it covers. The second one, the one on the left, is useful if you have two planets or two moons or two things that are rotating around. I should call them satellites. I shouldn't call them moons. Technically, only the moon is the moon. The moon is a satellite that goes around the Earth. So, but I think everybody gets what I'm talking about. All right. Let's see here. Any other questions? I feel like I'm missing something with gravity, but I don't quite remember what I'm missing. Oh, escape velocity. We literally just talked about it on the homework, so there might be an escape velocity problem. Oh, we're almost out of time. That's going to be velocity equals the square root of 2gm over the radius of the Earth. We'll talk about energy next time, and we're totally out of time. So I'll go ahead and stop the recording right now.